All right, Math 111, good morning. Today we're going to talk about section 4.2, solving compound inequalities. Oh, by compound inequalities, we mean inequalities that are combined in one way or another with other inequalities. We're going to talk about two things today, double-sided inequalities and OR type inequalities. As we'll see, double-sided inequalities are really logically equivalent to an AND statement, mathematical AND statement. So basically we're going to cover both types and OR inequalities today. Alright, let's jump right in and get started. Let's talk about a double-sided inequalities. We'll do those first. And by that, let me give you an example of this. Let's say we've got a statement like this. Alright, double-sided inequalities for obvious reasons. Basically, we've got an inequality that might look like something we saw in section 4.1 combined with another inequality that we might see in section 4.1 joined in one statement. So really we're asking us to solve two equations, or I should say two inequalities, simultaneously. Alright, hence the name double-sided inequalities. Alright, what I'm going to seek to do here is isolate my x variable in the middle. Get x in between with two numbers, boundary values on either side, at which time we can determine our solution set. So what I'm going to do here, to isolate x in the middle, I'm going to subtract 5 from all three pieces of this double-sided inequality. All right, and that will give me minus 8 is less than or equal to 2x is less than positive 2. All right, remember our goal in this type of double-sided inequality is to isolate x in the middle, get it all by itself, and I'll divide each element here by positive 2, and I leave the inequality arrow alone because I'm dividing by a positive. That'll give me minus 4 is less than or equal to x in between, which is in turn less than 1. Alright, so this is really two inequalities in one. We can say x is greater than minus 4, and we can also say at the same time x is less than 1. Alright. So let me graph that set of numbers on the number line. And let me get another color here. Minus 4. Well, let's see. Let's graph this part first. X is less than 1. Well, I usually put 0 as a milestone. I'll put 1 somewhere right of 0 on the number line. So I'm going to have an open boundary at 1. So I'll indicate that with an open circle. Let's see. And simultaneously, minus 4 is less than x. If I read this circle right here, right to left, it's x is greater than minus 4. X greater than or equal to minus 4, I should say. So greater than or equal to means to the right of, with a closed circle at minus 4. So this graph indicates all real numbers between minus 4 and 1, including minus 4, but excluding positive 1. So if I ask you to solve and graph solution set, I should write my solution set is all x values between minus 4 and 1. The boundary at minus 4 is included, and the boundary at 1 is not included. So here is my graph. So solution set and graph. And typically that's what the solution set of these double-sided qualities, double-sided inequalities will be. Basically a interval of numbers on the real number line bounded above and below by values you'll be determined in the solution. Let's try another one. Solve and graph solution set. Another double-sided inequality. Alright, my goal in these double-sided inequalities is to do algebra type things, namely add, subtract, multiply, and divide, to isolate x in the middle and get numbers on either boundary. Alright, so to that end I would probably add 8 to all three elements here first. I'll get 3 on the left hand side. The minus 8 plus 8 cancel out, 3x in between, and 8 plus 7 is 15 on the right side. I'll divide all three of these elements by positive 3. Leave the inequality arrow alone. When you divide by a positive, you leave it alone. And there's my solution set. I'll label it. So again, I can read this, I can graph this. I want all numbers that are less than or equal to 5. Well, less than 5 means to the left of 5 on the number line. I'll close in the boundary at 5 and start shading in all numbers to the left. Now clearly I'm going to have to stop. Where am I going to stop? Well, you stop at 1 because the other condition here is that x is greater than 1, right? If 1 is less than x, x is greater than 1. And notice that's a greater than or equal to. So I'll shade in that closed circle as well. So this is really describing all real numbers between 1 and 5, including the boundary values. All right, so let me make this a little neater now. My graph of the solution set looks like this. And let me redraw the solution set here, or restate the solution set. It's 1 is less than or equal to x, which is in turn less than or equal to 5. There is my solution set. Alright, let's try another one. Solve and graph solution set. Minus 2 is less than minus x plus 3 is in turn less than 5. Alright, again my goal is to isolate x in the middle element, and to that end I would probably subtract 3 from each piece as a first step. Alright, this gives me the resulting statement. Minus 5 is less than minus x, which is in turn less than 2. Alright, I'm going to multiply each piece by minus 1. Let me write this down. Multiply through by negative 1. You want to solve for x in between. And when you multiply by a negative, you must reverse all the arrows. Well, here you've got 2. You've got to reverse both the arrows. And remember, that's an easy step to forget. So if I multiply through by negative 1, multiply each piece of this inequality by negative 1, I've got to reverse both inequality directions. Alright, so here is my solution set. And again, to graph it, I suppose it's easiest to read it a step at a time. Now, let's take a look at this statement here. X is greater than minus 2. And what does this statement say? It says x is less than 5. So I want all numbers greater than minus 2 and less than 5. Now, I can easily graph that. X greater than minus 2 means to the right of minus 2. Showing an open circle at the boundary. And similarly, x is less than 5. Less than 5 means to the left of 5, and shade in all values simultaneously to the left of 5. So here is the graph of my solution set, and let me restate the solution set. 5 is greater than x, which is in turn greater than minus 2. Here's my graph. There's my solution set. Okay. Alright. Let's try another one with some fractions in it. This is from the homework list. This is number 66 on page 345 in our text. As we know, equations and inequalities don't always have whole numbers to deal with. Sometimes you got to deal with fractions. Alright, minus 4 is greater than 2/3 x minus 2, which is in turn greater than minus 6. Solve and graph solution set. Alright, here I would probably add 2 to each piece of this double-sided inequality. I'll get minus 2 is greater than 2/3 x. The minus 2 and plus 2's cancel, which is in turn greater than minus 4. Alright, I want to solve for x in between, so I'm going to multiply each piece by positive 3. And I leave the inequality arrow alone because I'm multiplying by a positive. On the left, I get minus 6. In the middle, the 3's cross cancel and I get 2x. On the right, I get minus 12. Alright, now, one more step. I'll divide both sides by positive 2. Or all 3 sides, really, by positive 2. Minus 6 over 2 is minus 3, is greater than 2 over 2's cancel. I get x in between, which is greater than minus 6. So here is my solution set. It's telling me x is greater than minus 6, and simultaneously x is less than negative 3. Let me see if I can squeeze this graph in here. X is greater than minus 6, so I'll put minus 6 here. An open circle at minus 6, meaning the boundary is not included, and shade in all values to the right until I hit minus 3, because this tells me x must also be less than minus 3. Alright, so there is my number line graph of this solution set. Let me label it graph. And if I want to redraw the solution set, minus 3 is greater than x, which is in turn greater than minus 6. Okay? Alright, let me get a fresh screen here. Let's try another one from the homework list. This is number 70, also on page 345. Giving you a leg up on the homework here. Oh, this pretty much represents the upper limit of difficulty. Actually, I think this is the last problem in the homework list. I got a fractional expression involving x in between and 2 numbers outside. Again, a double-sided inequality. Really an AND statement. And I'm going to multiply each element by positive 2. Alright. I suppose I should go ahead and write that out. Multiply each element in this inequality by positive 2. Alright. On the left, 2 times minus 2 is minus 4. In between, the 2's cross cancel, and I'm left with this numerator, 5 minus 3x in between. And on the right, 2 times 2 is positive 4. Alright, I'm now going to subtract 5 from each piece. I'll get minus 9 less than or equal to minus 3x. the 5's, the minus 5's cancel out, is less than or equal to negative 1. Now I'm going to divide each piece by negative 3. Now you got to be careful here. I'm dividing by a negative. Each piece here. And when I divide or multiply by a negative, you must reverse the arrows, and here you got two of them. So these turn into, instead of less than or equal to, now they're greater than or equal to. And of course I can simplify these expressions. Minus 9 over minus 3 is positive 3. Is greater than or equal to, well, the minus 3's cancel. I've got x in between. And on the right hand side I get negative 1 over negative 3 is positive 1/3. So there is my solution set. 3 is greater than x, which is in turn greater than 1/3. Alright, so how I usually graph these, I take it a piece at a time. If I look at that piece, it tells me x is greater than 1/3. Alright, that means everything to the right of 1/3, and I include 1/3 because I've got a equality included there. Greater than 1/3 until I hit what? Well, this statement here tells me x is less than 3, right? X is less than or equal to 3. So I'll go up to 3, positive 3. I draw a closed set here as well. So really this statement, 3 is greater than x, which is in turn greater than 1/3, specifies all real numbers on the number line between 3 and 1/3. Okay. Alright, so that's 5 examples of double-sided inequalities. One more topic, one more subtopic I want to talk about today, and that is Ortype inequalities. Right, remember, double-sided inequalities are really end statements. You're being asked to solve two inequalities simultaneously. Right? Well, we've got another type of inequality called OR inequalities, and typically those are stated in fashion like this. Let's see, x over 3 is greater than 2 over 3, or minus x minus 2 is greater than 3. And when you see two statements like this connected with an OR statement, a logic OR statement, well, that basically means you have to solve each inequality simultaneously and then join them, or what they call union them, with this OR statement. Alright, this first one, this one on the left, is easy to solve. I'll just multiply both sides by 3. Leave the inequality arrow alone. I'll get x on the left is greater than 2 on the right. Alright, I connect that with an OR statement to this statement. Right? Minus x minus 2 is greater than 3. I'll distribute this negative sign on the left-hand side. I'll subtract 2 from both sides. Minus 8 is minus x is greater than positive 1. And here I'll multiply both sides by negative 1. You want to solve for x, not negative x. So here is my resulting statement. I have the set described by this statement. X is greater than 2, or x is less than minus 1. Alright, what does that mean? Well, what does OR mean? The word OR means, well, your solutions are in one of these sets or the other, one of these statements or the other. Well, what does greater than 2 mean? If I look at this branch here, greater than 2 means everything to the right of 2, not including 2. So I can shade all numbers right of positive 2, indicate this element of my solution set. Or x is less than minus 1. Well, minus 1 is down here somewhere. I can say less than means left of, and draw an open circle at negative 1 and shade in everything to the left. So typically in these OR type situations, you'll end up with broken sub-intervals of the real number line going off to infinity in either direction with some unincluded set in between. Alright, so if I again want to say this is my graph of the solution set right here, and I can say my solution set here is x is greater than 2 or x is less than -1. There is my solution set. For this answer, you need to connect these with an explicit OR statement, else it will be marked wrong. Okay? OR means OR. Alright, let's try another one similar to this. Solve and graph solution set. Let's see, x over 2 is greater than 2, or -3 times x minus 2 is greater than 0. Make that a little clearer there. So I've got two inequalities linked together with an OR statement. So again, what I'll do is solve each independently and then join them together or union them in a logic OR statement to determine my solution set. Alright, not much going on in this one. On the left branch, I'm just going to multiply both sides by 2, and I get x is greater than 4. Alright, I'm going to have to solve this right branch then independently. Applying my distributive law, I get -3x plus 6 is greater than 0. I'll subtract 6 from both sides, and if I divide, let me write this out, both sides by -3, I must reverse. Get another color there to accentuate that. I must reverse my inequality arrow. Okay? Alright, one more step really. I get x is then less than +2. So here's my solution set. I'll rewrite it. X is greater than 4, or x is less than +2. Alright, let me rewrite that. Solution set. X is greater than 4, or x is less than 2. Right, there is my solution set. So what I'll do is graph both of these inequalities independently on the number line and then union them and say my solution set includes the solutions to both of those inequalities. X is greater than 4, well, that means everything to the right of 4. Alright. On test day, be nice and explicit, show clear graphs. X is less than 2, well, we know what that means. Less than means left of, and again, open circle at +2, shade in everything to the left. Okay, so there's my solution set, and there's the graph of our solution set. Alright, one more, we'll call it a day. Let's get something a little harder here. This is from your homework list. Solve and graph solution set. X over 3 minus x over 4 is greater than 1/6, or x over 2 plus 2 over 3 is less than or equal to 3/4. Now don't panic. Students will see something like this on test day, and the tendency is sometimes to panic. Alright, these inequalities have fractions in them. I want to get rid of the fractions, and we do that by multiplying by the LCM of all those fraction denominators. And the least common multiple of 3 and 4 and 6 is, of course, 12. Alright? You've got to apply your distributive law now. 12 times x over 3. Well, 3 cross cancels into 12 4 times, and 4 times x is 4x. I've also got to multiply 12 times x over 4, right? So minus 4 goes into 12 3 times x is x. So all the fractions go away on the left-hand side. On the right-hand side, 1/6 times 12, 6 goes into 12 twice, and 2 times 1 is 2. Looks better already. Let me stay with the left branch of this OR statement and solve this. Only one more step really. 4x minus 3x is x, and x is greater than 2. on the left branch. Okay? Similarly, on the right-hand side, I can see 12 is the least common multiple of 2 and 3 and 4, is it not? I'm going to multiply both sides by positive 12. Leave the inequality arrow alone. 2 goes into 12 6 times. 6 times x is 6x. Plus 3 goes into 12 4 times, and 4 times 2 is positive 8. On the right-hand side, 4 goes into 12 3 times, and 3 times 3 is 9 on the right. I'll subtract 8 from both sides. I get 6x is less than or equal to 1, and if I divide both sides by positive 6, I get x is less than or equal to 1/6. Alright, now let me rewrite that. X is greater than 2, or x is less than or equal to 1/6. This is my solution set for the above inequality. Again, really two solution sets to two different inequalities connected with a logic OR statement. Alright, let's graph the solution set now. Greater than 2. What does greater than 2 mean? Well, everything to the right of 2. Open boundary at 2, shade in everything to the right. Or x is less than or equal to 1/6. Well, where's 1/6? Well, it's on the same side of 0. The relative position doesn't matter much as long as I show my boundaries correctly. I'll show a closed-in boundary, closed-in circle at 1/6, and less than means to the left of. And now typically this is how your solution sets to OR type problems will look. Alright. Two infinite intervals broken up, a broken up subinterval on this number line. So there's my solution set. There's the graph of my solution set. Alright, we're approaching the 28-minute point, so we'll call it a day. And this concludes section 4.2, Solving Compound Inequalities.